Welcome to the tutorial session of the second week. In tutorial 2, we are focusing our attention on understanding pipeline hazards. Let us move into the first question. It's basically a set of statements. We have to tell whether it is true or false. Which of the following statements is or are true? Raw data hazard could be reduced by operand forwarding. So that's the first one. So consider the set of the instructions that is been given here. This add instruction is, so add instruction then sub, and we know that add produces a result which is to be written in R1 and all other subsequent instructions are going to read from R1. So there exists a raw dependency, and you can see that by the concept of operand forwarding, we are forwarding the result from one functional unit to another, that is from output of ALU to input of ALU and from output of mem stage to the input of ALU. So because of this, I am not having any stall. So the statement raw data hazard could be reduced by operand forwarding is true. The second one is a normal in-order 5-stage MIPS pipeline can achieve an IPC larger than 1. So this is how you visualize a pipeline. In every cycle, I am going to fetch an instruction, and in every cycle, in ideal case, we are going to complete one instruction. So on an average, if you look at every cycle, I am completing one instruction. So the statement, a normal in-order 5-stage MIPS pipeline can have an IPC, instructions per cycle, larger than 1. I cannot complete more than one instruction per cycle in a normal in-order 5-stage MIPS pipeline. So an IPC larger than 1 is impossible. So the second statement is false. Moving on to the third statement, for a MIPS instruction, store R2 16 of R3, some contents stored in its IDEX pipeline register will bypass the EX unit directly to the EX mem pipeline register. So let us try to understand what is the store instruction. The contents in the register R2 has to be stored into memory, and the address to which the storage happen is 16 plus content of R3. Let us say how this happens. Store R2 16 of R3. So your instruction is being fetched. So at the end of the fetching stage, your instruction is available here. You fetch the contents of R2 and R3. So R2 and R3 is been now going into IDEX register. Now 16 and R3 is added in the ALU to get effective address. In the meantime, the contents of R2, which is already available in the IDEX register, that moves to EX mem register. So all the contents that is available in the IDEX register are not used by the ALU. Through this line, some of the content, it's basically the content of R2, that is the value to be stored in the memory, which is already locating in R2, will move from IDEX register to the EX mem register. So the statement for a MIPS instruction store R2 16 of R3, some contents stored in its IDEX pipeline register will bypass the EX directly to the EX mem register is true, the content of R2. The fourth one is a normal 5-stage in-order RISC pipeline without operand forwarding can have raw and war hazards. See, this is the general pipeline that you have seen, and this is raw hazard, and here we have the war hazards. So the statement, the last statement, a normal 5-stage in-order RISC pipeline without operand forwarding can have raw and war hazards. That is false. So here, which of the following statements are true? The answer is 1 and 3. So now we will look into the statements like this. The next set of true or false statement. Which of the following statement is or are false? For a MIPS multi-cycle floating point pipeline, the initiation interval of floating point mul is larger than that of floating point add. Let us see what is there. So the initiation interval is being defined as how much cycle has to be elapsed if you wanted to use the functional unit again. So the integer ALU, the floating point multiplier, and the floating point adder has an initiation interval of 1. But they differ in latency. There are 4 stages in the FP adder, and there are 7 stages in the integer or floating point multiplier. So the statement for a MIPS multi-cycle floating point pipeline, the initiation interval of floating point mul is larger than that of floating point add is wrong. They both have the same initiation interval, but however, FP mul has a larger latency than an FP add. Now, wow hazard cannot happen in a MIPS multi-cycle floating point pipeline. So, wow hazard is write after write hazard. So, consider the case that when you have a MIPS multi-cycle floating point pipeline where some instructions are longer. The first instruction is a multiplication. So, it takes 11 cycles to complete. Let us say the second one is add, which will take only 8 cycles to complete. So, surely even though we are fetching instruction in order, the execution is out of order or the completion is out of order. So, when the completion is out of order, there is always a possibility that we can have write after write hazards. So, the statement in a MIPS, a wow hazard cannot happen is false. Wow hazard will happen because instructions are completed out of order. Moving on to the third one, in a MIPS multi-cycle floating point pipeline that supports operand forwarding, there will be 7 stalls between a pair of adjacent multiplication instructions that has a raw dependency between them. So, this is what is the general structure of this multiplication unit. You have the first instruction which starts at 1 and then it completes only at 11. If the second instruction is going to have a raw dependency on it, then the M1 of the second instruction can happen only after M7 of the previous instruction. So, there will not be 7 stalls, there will be only 6 stalls between them. So, the statement that there are 7 stalls between a pair of adjacent multiplication instruction that has a raw dependency is wrong. If a 32-bit value 0x12345678 is stored in memory byte addresses 2000, 2001, 2002 and 2003 in big endian format, then the location 2001 holds the value 56. Let us try to understand what you mean by big endian and little endian. In big endian, when you store a 4 byte data into 4 continuous memory location, if MSB is stored in the lower address and LSB is stored in the higher address, then that is known as big endian. If the LSB is stored in lower address and MSB is stored in the higher address, that is called little endian. So, the statement when you have a 32-bit value 1, 2, 3, 4, 5, 6, 7, 8 is going to be stored in locations 2000. So, these are the locations 2000, 2001, 2002 and 2000. So, this is 2000, 2001, 2002 and 2003 and our value is 0x 1, 2, 3, 4, 5, 6, 7, 8. And then we are going to store them in big endian format. So, once you store in big endian format, the MSB is stored in the lower address. So, 0x12 gets stored here, 3, 4 gets stored here, 5, 6 gets stored here and 7, 8 will get stored here if it is in big endian format. So, what they are telling is 2001 holds 56. So, 2001 is holding 34. So, the statement that 2001 holds 56 is wrong. So, all the 4 statements are wrong. So, the answer would be 1, 2, 3 and 4. They all are false. So, in the first 2 questions in today's tutorial, there were 4 statements given and we were asked to check whether those statements are true or false. And we have now seen by correlating with the theory concept that we learned in the lectures to ascertain whether these statements are true or false. So, to answer these kind of questions, you require a thorough reading of the material, the video that is being covered and supplementary reading of the textbook material in which these topics are discussed. Let us now move into pipeline hazards. Let us try to understand this question. Given a non-pipelined architecture running at 1.5 gigahertz, which will take 5 cycles to finish an instruction. You want to make it pipelined with 5 stages. When I am having pipeline interface register, due to the hardware overhead, the pipeline design will operate only at 1 gigahertz. So, you have to understand your non-pipelined design will operate at 1.5 gigahertz. So, the clock is 1 divided by 1.5 gigahertz, whereas the pipeline design is operating at 1 gigahertz. Now, 5% of the memory instruction costs a stall of 50 cycles. 30% of branch instruction costs a stall of 2 cycles. And load ALU combinations, we have seen that if there is an ALU operation immediately after the load operation, they cause a stall of 1 cycle. Assume that in a given program, there exists 20% of branch instructions and 30% of memory instructions. 10% of instructions are load ALU combinations. What is the speed up of the pipelined design over the non-pipelined design? This is a question that is been given. So, let us try to understand what the question is all about. You have an unpipelined design wherein the timing is given 1.5 gigahertz of clock. We have a pipeline design which can operate only at 1 gigahertz, but the idea of pipeline is the base CPI is 1. Every cycle 1 instruction is getting completed. In the case of an unpipelined version, it takes 5 cycles to complete an instruction. Now, in the pipeline, we will be having hazards. The first kind of hazard is called the memory issue, wherein you are trying to fetch something from the instruction from memory, you are not getting. So, for certain percentage of memory instructions, it will be hit in the memory. For certain percentage, it may be a miss in the memory. So, whenever you miss, you are going to have 50 cycles of stall. Similarly, when you come to branches, there are hazards for certain fraction of branches, and there is a data hazard for load ALU combinations, that is for certain percentage. Now, we have to find out what is the overall execution time in this case. So, the CPI of the unpipelined is 5. So, it takes 5 cycles to complete an instruction. The unpipelined version is working at 1.5 gigahertz, roughly 0.667 nanosecond, and the pipelined version is running at 1 nanosecond time. Now, execution time of the unpipelined is CPI into clock cycle time, execution time for one instruction. So, it takes 5 cycles to complete one instruction, and each cycle is 0.6667 nanoseconds. So, roughly it is 3.33 nanosecond it will take to complete one instruction in the unpipelined design. So, the effective CPI in the case of pipelined instruction is the base CPI, that is 1. In every cycle we complete one instruction plus whatever is the stalls that is happening. Now, what are the kind of stalls? We have memory stalls, we have branch stalls, and you have load ALU stalls. Now, memory stalls, so what is the base CPI? Base CPI is 1, that means every cycle 1 instruction is getting over. Memory, you have 30% of instruction that are memory, but 5% of memory instruction will incur 50 cycle stall. So, it is 0.3 into 0.05 into 50. Coming into branch, we have 20% of the instruction that are branch, but 30% of the branch instruction only will create hazards. It will create 2 cycle of stalls. Coming into load ALU, 10% of load ALU instruction combinations are there, and they are going to create 1 cycle stall. So, it is 1 plus 0.75 plus 0.12 plus 0.1, roughly it is 1.97 is the effective CPI in the case of pipelined design. So, execution time in the case of pipelined is CPI into clock cycle time. CPI is 1.97 and it is going to operate, the pipelined version is going to operate at 1 nanosecond clock. So, it is 1.97 nanosecond per instruction. Now, what is the speed up? Speed up is execution time of unpipelined divided by execution time of pipeline. So, 3.33 which we have already computed divided by 1.97, that is equal to 1.69. Now, pipeline hazards. Next question. A program has 2000 instruction in the sequence load, add like that. So, the first, third, fifth, seventh, all odd number instructions are load, odd, and all even number instructions are add. The add instruction depends on the load instruction right before it. The load instruction depends on the add instruction right before it. If the program is executed on a 5-stage pipeline, what would be the actual CPI with and without operand forwarding? So, without operand forwarding technique, let us try to understand how the instruction will flow. So, this is the sequence of instruction. You have load, add like that. Now, the peculiarity is this add is dependent on the load. So, the result of load will happen only at the write back stage, and since there is no operand forwarding, the add can get its data only after the previous load has returned the result, because there is a dependency between them. That means the ID of an add statement can happen only after the write back stage of previous load. So this add is going to write the result here, and this load is dependent on the previous add. So the ID stage of a load can happen only after the write back stage of the previous add is over. Similarly, you can see that the ID of every instruction can happen only after the write back stage of the previous instruction. So ID of nth instruction can be only after the WB of the n-1th instruction. So there are 3 stalls. You can see there are 3 stalls in each of the instruction if you follow this pattern. So instructions reaches the write back stage. The first instruction reaches write back stage at 5, second reaches at 9, third reaches at 13, fourth reaches at 17. So it's a pattern that you can see 5, 9, 13 like that. So the last add instruction will reach the WB stage. So the first instruction reaches at 5. Then I have another 1999 instructions more. Each will be completed at a difference of 4 clock cycles. The first instruction will reach write back stage at 5, and then 5 plus 1999 more instructions which will take 4. So the answer is going to be 8001 clock cycles. So if you look at the CPI value, then it will be 8001 divided by 2000. So it's roughly going to be 4, because you know that every cycle one instruction is getting over, and you have 3 stalls extra. So the average CPI is going to be 4 in this case. Now we will see what is with operand forwarding. So if it is with operand forwarding, we can see that load add dependency. So this add instruction is dependent on the load. So add instruction will get the data only at the end of mem. So mem is forwarding to EX. So that is going to incur 1 cycle stall here. Similarly, this load is dependent on the add, but there it is not a problem. Again, this is dependent on the previous load. So every add after load has a stall, but load after add do not have a stall. That's a peculiarity. The first instruction complete at 5, second at 7, third at 8, fourth at 10, like that. So if you look at the pattern, instructions reach write back at clock cycles 5, 7. So all the red color markings, they are the load instruction. So load instruction getting completed at 5, 8, 11, 14 like that. Add instruction is getting completed at 7, 10, 13, 16, etc. The last instruction is add. So add, we look into the pattern of add only. We look into only the blue. So first add instruction is getting completed at 7. We have another 999 add instructions more. Each will be completing at a clock cycle shift of 3 cycles. So at 3004, we have the last add instruction completing. So what is CPI? 3004 divided by 2000, it's roughly 1.502. So given in this question, what we have seen is, if there is a sequence of load and add combinations, then if it is without operand forwarding, then every instruction has a stall of 3. So normal, an instruction take 1 cycle to complete plus 3 more cycles. So on an average, the CPI is 4. And when you come to the operand forwarding mechanism, the second instruction is dependent on the first instruction. Every add is dependent on the previous load, and there is a 1 cycle stall. But every load that is dependent on an add, since there is operand forwarding, there is no stall that happens. So every alternate instruction will have 1 stall. So when you have 2000 instruction, you have 1000 stalls. So close to 3000 would be the total number of cycles to complete. So 3000 divided by 2000, your average CPI is going to be 1.5. Now let us move into another question, which is a branch prediction question. Consider the last 16 actual outcomes of a single branch, where T means branch is taken and N means the branch is not taken. So this is the pattern. So if the statistics of what is the outcome of a branch is been collected. So T means taken. So it's taken, taken, not taken, not taken, like that for the last 16 outcomes. This is the latest one. The latest one was taken. The first one was taken. Second time the iteration was taken. Third was not taken. That's the way how we have to interpret the sequence. A two-level branch predictor of 1-2 type is used. Since there is only one branch in the program indexing to BHT, branch history table with the PC value is irrelevant. So, 1-2 predictor means last one outcome of a branch is being used to index into the table, and we are using a 2-bit predictor. So, MN predictor, basically if a branch is being mentioned as MN predictor, M stands for last M occurrences of the branch is being used to index into the branch history table, and each entry has an n-bit branch predictor. So, we are asking how many mispredictions are there and which of the branches in the sequence would be mispredicted. Fill up a table for 16 branch outcomes. So, we are basically using a 2-bit predictor. So, when the value of the predictor is 0, 0 or 0, 1, we predict that the branch is not taken. When the value is 1, 1 or 1, 0, we predict that the branch is taken. So, we have to keep this in mind. Whenever the value is 0, 0 or 0, 1, the prediction is branch will not take, and whenever the value is 1, 1 or 1, 0, the prediction is branch will be taken. Now, let us see about transition. When we are in 0, 0, we predict that branch is not taken, but if actually the branch is taken, then from 0, 0 state, I have to correct my state as 0, 1. When I am in 0, 1, then if branch is taken, actually if it is taken, then I change my prediction value to 1, 1. Similarly, when I am in 1, 1 and if the actual outcome is not taken, then I am moving into 1, 0. Similarly, when I am in 1, 0, when the branch is actually taken, I move into state 1, 1. So, this is the transition diagram that has to be familiar with us. Now, what happens here is, here it has been mentioned that what will happen to the last 16 outcomes of this branch. So, this will tell you what happened to the branch. So, the first iteration the branch was taken, second iteration branch was not taken, like that the 16th iteration branch was taken. Now, let us see this table. This table looks a bit clumsy when you try to work out these questions for the first time. I make it more simple. This is your branch history tables entry. So, the branch history table has 2 columns. The first column tells when the branch entry is not taken, you have to consult the first column. When the branch entry is taken, then you have to look into the second entry. So, it is basically a 2-entry table. So, this is the 2 entries. When, and I mentioned that we are mentioning a 1-2 predictor. So, you look into what is the outcome of the last branch. If the outcome of the last branch is not taken, then refer this. The last branch is taken, then refer the second entry. So, to interpret into the table, if the last branch was actually not taken, refer this entry. If the last branch was actually taken, then refer the second entry. So, referring into first and second entry is the most crucial thing as far as working with this branch table is concerned. Now, the initial configuration of the branch is 00/11. So, my first one is, my initial condition is n, last outcome. Now, I am referring into this one. Since the last outcome, for the initial case to start with, let us assume that it is not taken. Since it is not taken, I refer into the first entry 00. Since the entry is 00, we have to understand that if the entry in the table is 00 or 01, then the prediction is not taken. If the entry is 10 or 11, then the prediction is taken. So, since the entry is 00, I predict it as not taken. But what actually happened with the first branch? The first branch was taken. So, my prediction was not taken, but the actual outcome was taken. That is a misprediction. I predict that branch will not take, but actually the branch was taken, and that is known as misprediction, yes or no. This is a mispredicted case. Now, when I move into the next entry, I have to make some changes. My state was 00, but the prediction went wrong. When prediction went wrong from 00, I move to 0, 1. That is what has been the change that you see. So at the end of the first row, the table gets itself updated to 0, 1 / 1, 1. Why this is 1, 1? I am not going to make any change to that entry which I have not referred. I have referred only the first entry 0, 0. And first entry 0, 0, based upon that I predicted it was not taken. Actual outcome was taken. So it's a misprediction. Whenever there is a misprediction, I have to change the state. Now, the second row works with the new updated table. So what's the new table? The new table is 0, 1 / 1, 1, and this is already taken. Now the last outcome of the branch was taken, so this will get repeated. So these both will be same. Whatever was the last outcome that is been entered here. So the last outcome was taken. Since the last outcome was taken, I look into the second portion of the table. When the last outcome is not taken, look into the first portion of table. Last outcome is taken, look into the second portion of the table. The second portion is 1, 1. That means a prediction will be taken. Whenever this shows that whenever the entry is 1, 1, the prediction is taken. The actual outcome is also taken. That means it is not a misprediction. So in this case, the third row is same as this. Now the last outcome was taken. How will I get this? This was the last outcome. Last outcome was taken. I refer into this. It is predicting that the branch will be taken. But actually the third time the branch was not taken. So that is a misprediction. Once it is a misprediction, from 1, 1, when I mispredict, I move to 1, 0. That is what is happening here. So that's a change that is being reflected. I move into 1, 0. Now I continue with the fourth iteration. The previous one was not taken. So I go here. This is not taken. Since it is not taken, I refer to the first half. The first half is 0, 1. 0, 1 indicates not taken. Actual outcome was also not taken. So there is a perfect match there. So when at 0, 1, when the branch was not taken, then we have to understand that it will go back to 0, 0 state. So this is our table. When you are in 0, 1, when the branch is not taken, I move into 0, 0. And then the previous outcome was not taken, so I continue. So to fill up this table, whatever is here, the same thing will get repeated in the next row. This is the outcome. That outcome is used for the subsequent rows. So if you continue like that, we have to understand, I have to update only that entry which I have referred. If the entry that I have referred is correct, then I make the predictions, I look into what is the outcome. Based on the outcome, I make appropriate changes and update the entries downward. This is the way how it is to be flourished. So wherever this green color that is being shown, these are cases where the prediction and the outcome was matching. In all other cases where the S is marked, these are cases where I got mispredictions. So I got total of 10 mispredictions from this entire setup. So what is been given here is, you have given a structure of a table. This is a 1, 2 predictor. So last one occurrence only is being checked, and based upon last one occurrence, if the last occurrence is not taken, you refer into the first portion of the table. If the last occurrence is taken, you refer into the second portion of the table. Now the contents of this table, you look into 0, 0 or 0, 1. Then the prediction is not taken. If the content of the table is 1, 0 or 1, 1, then the prediction will become taken. Now you see, correlate with what is actually happening. This is a sequence which is telling what is the outcome of the branch. If they are perfectly matching, then there is no misprediction. If there is a mismatch, so the value that we predicted and the actual outcome is different, then there is a mismatch, and then we have to correlate that. So with this, we come to the end of the tutorial. In this tutorial, we have seen about how to handle with the hazards. Few true or false statements were there, and then we had few numerical problems in handling with the hazards, and then some dependency issues with and without operand forwarding, and towards the end we had branch predictor. This week also we will put up some short exercise questions also for you to work on with respect to branches. Thank you.